Being invisible, the Earth's atmosphere has eluded human inquiries for centuries, although its ever-changing nature has always been the subject of daily discourse. In this century, the atmosphere has changed significantly faster than it has at any time in human history. These changes, already well known to the scientific community, are now making increasing demands upon the public awareness as their negative effects become more and more evident. Surprisingly enough, these important phenomena arise from modifications in the composition and concentration of the minor constituents of the atmosphere, which are known as trace compounds. These trace compounds, gases and particulate matter, can be emitted in the atmosphere by natural sources. Volcanoes emit large quantities of sulfur dioxide and particulate matter, predominantly in the form of ash. The oceans, on the other hand, are the major source of biogenic reduced sulfur species. And forests release a wide variety of hydrocarbons to the atmosphere. In the last 100 years, the emissions resulting from human activities have increased significantly. These added emissions are primarily responsible for the current changes in the atmosphere. Human activities, being confined to the Earth's surface, profoundly affect the composition of the troposphere, the lower part of the atmosphere, which is critical to the life of the planet. The troposphere can be seen as a highly complex reaction chamber, in which trace compounds are processed and new species are produced. The chemical transformations depend upon a variety of conditions, such as local meteorology and general circulation, concentration of trace gases and atmospheric particles, intensity of solar radiation, and the presence of clouds, fogs, and precipitation. In particular, the processes occurring in fogs and clouds are of great interest because they are suspected of being the crucial link between emission of pollutants into the atmosphere and subsequent deposition as acidic species in precipitation. Clouds and fogs constitute a so-called multi-phase atmospheric system, insofar as gas, liquid droplets, and solid particles are simultaneously present. Gaseous and particulate trace compounds undergo a variety of processes. Some are physical in nature, such as condensation of water vapor onto particles to form liquid droplets, dissolution of gaseous species into the droplets, capture of other particles by the droplets. Also, chemical transformations occur. Gas phase reactions are frequently catalyzed by sunlight, as in the case of hydroxyl radical formation from ozone photolysis. The reaction products can subsequently be incorporated in the droplets. Other chemical reactions occur in the liquid phase, as for example, bisulfite oxidation by hydrogen peroxide to form sulfuric acid. All these processes are interdependent, and this multiplies the overall complexity of the system, making it difficult to separate and evaluate each single contribution. On the other hand, the elucidation of the nature and extent of these chemical and physical transformations is absolutely necessary to current efforts at modeling cloud processes responsible for the acidification of precipitation. Several laboratory studies using precisely controlled conditions have contributed to the understanding of many of the processes outlined above. But there still remains a dearth of experimental studies in the real environment. Studies of physico-chemical processes in the real atmosphere are best realized in a well-defined multi-phase atmospheric system such as radiation fog, which occurs under conditions of high atmospheric stability and very low wind speed. While the temperature of the air usually decreases with height, in high pressure and clear sky conditions, the radiative cooling of the Earth's surface causes the layer of air in contact with the ground to become colder than the air aloft, creating a temperature inversion. When the temperature of the air drops below the dew point, then fog forms. Airborne pollutants are trapped within the fog layer, with residence times of the order of hours. It is therefore easy to see why radiation fog is an ideal natural laboratory for the study of physico-chemical processes in a highly stable system which contains gas phase components, atmospheric particulate, and liquid droplets. To study these processes, a field experimental program was established a few years ago in the Po Valley, which is a large alluvial plain in northern Italy of about 85,000 square kilometers. This plain is surrounded on three sides by high mountain ranges, the Alps and the Apennines. During the fall-winter months, the orography of the valley favors, in high pressure conditions, the establishment of strong temperature inversions in the lower layers of the atmosphere and the formation of widespread radiation fogs. Fog occurrence in this area can be as high as 30% during the period from November through March. At the field station of San Pietro capofiume, in the eastern part of the valley, several fog field experiments had been carried out in the previous few years with the participation of research groups from several European countries and from the US. In November 1989, several research teams from 5 European countries gathered at the field station for a major experiment that lasted 1 full month. To parameterize the physico-chemical processes occurring in fog, it is necessary to measure the concentrations of important chemical components in the gas, droplet, and particulate phases, and the thermodynamic conditions of the atmosphere at the time. In previous campaigns, only ground-level measurements had been performed. During the present experiment, a particular effort was made to extend the measurements in vertical, using the 50-meter tower available at the site, equipped for meteorological, microphysical, and chemical measurements. In fact, the concentration and distribution of gas and aerosol components on a vertical scale is not uniform, but is determined by the chemical and microphysical processes occurring in the atmospheric system. To give a complete description of the system, most measurements were carried out continuously round the clock. Droplet sampling and characterization were initiated at the onset of fog and continued throughout the event. The fine meteorological structure of the first 50 meters was determined measuring temperature, relative humidity, solar radiation, wind speed and direction at 5 different levels on the tower. Since soil conditions are important to the formation of fog, temperatures at 10 and 50 centimeters depth were continuously recorded. In addition, soil samples were taken to determine the humidity profile. An acoustic Doppler radar, SODAR, was used to obtain information on the vertical structure of the atmosphere over the first 500 meters. In fact, turbulence developing at the top of the fog layer can determine an exchange of chemical components between fog and the clear air above. 8 times a day, balloon soundings were performed. These soundings provided temperature, humidity, and wind vertical profiles necessary to the understanding of the fog formation and evolution. Particles of different size and nature influence in different ways the growth and chemical composition of fog droplets. Therefore, mass and chemical component distributions among different particle size classes were determined by multi-stage impactor sampling at different heights on the tower. Sulfur dioxide, nitrogen oxides and ozone were measured by commercially available continuous monitors. Air was drawn through Teflon manifolds placed at different heights. A computer-controlled valve system allowed for sequentially sampling to these monitors. For other key gaseous compounds for which standard automatic instruments are not available, indirect determinations are necessary. Gaseous nitric acid and ammonia play an important part in determining the acidity of fog droplets. The evaluation of these compounds can be compromised by artifact formation due to ammonium nitrate particle evaporation. Concentrations were therefore measured at different levels on the tower after collection by a denuder, which separates gases from particles on the basis of their different diffusivities. Solar radiation affects atmospheric gas and liquid phase chemistry. Therefore, total and UVB radiation were measured at the ground and at 50 meters height. Most processes occurring within the fog layer are a function of the liquid water content, which is a single macroscopical parameter in which the droplet size distribution is reflected. The forward scattering spectrometer probe is an instrument which provides the classification of fog droplets in 60 size ranges between 0.5 and 47 micrometers diameter. The instrument was run on the elevator of the tower for vertical profile measurements. To collect fog water droplets for chemical analysis, single-stage impactors were used at 4 heights. The design of the droplet collector was chosen among several possible prototypes on the basis of a series of field intercomparisons performed during the past few years and on wind tunnel calibrations. Other more complex prototype instrumentation, which was not suitable for being put on the tower on account of its size and weight, was installed at the ground. A counterflow virtual impactor provided an evaluation of fog liquid water content and of the size distribution of non-volatile material dissolved or suspended in the droplets. A tandem differential mobility analyzer was also used for the investigation of the hygroscopic nature of submicron interstitial aerosol particles. Additional instrumentation provided a continuous record of the size distribution of submicron aerosol particles. Continuous hydrogen peroxide and formaldehyde gas phase concentration were determined throughout the experiment using a continuous scrubbing fluorometric technique. All real-time data were acquired by individual computer systems, synchronized by a central unit, which also drives the automatic instrumentation. On the other hand, most chemical measurements are indirect and therefore imply a two-step procedure: selective sampling and subsequent analysis. In the case of non-stable compounds, the analysis must be performed immediately after collection. A laboratory was then set up at the field station for the analysis of fog water, pH and conductivity, major ions, organic acids, carbonyl compounds, and sulfur-4 species. Particulate samples and stable species present in fog water were analyzed at a later time by the different participants. While the results of this experiment will be made available to the scientific community in the near future, a first achievement can already be evidenced in this experiment. Collaboration among scientists is always a necessity. Environmental research, in particular, requires expertise from a wide range of disciplines. Neither scientists of one single group nor experts in one discipline could ever have conducted an experiment like this, aimed at the description of a complex atmospheric system. Scientific collaboration seems to defy one of the basic rules of arithmetic. 1 + 1 always equals something more than 2.